Okay, good afternoon. Welcome everybody. And today we have the pleasure to welcome Professor Duy H.N from Electrical and Computing Engineering, who is going to talk about what else? Machine learning. So, go ahead, please.
All right, thank you, Dr. Castillo. Thank you for joining me today. So today I would like to give a talk on our current and ongoing, some past and ongoing research work. And I would like to thank my PhD student. Most of the work I present today was done by my PhD student, Nguyen, as the CSRC program. And my collaborator at UCI, Dr. Squiders. So this is the outline of my talk. So first of all, I will give a very fast introduction about MIMO and massive MIMO and why and what we need from massive MIMO. And then I will discuss some technical challenges in massive MIMO system. And the next part, I cover some conventional methods, MIMO signal processing methods in massive MIMO system. And hopefully I can bring up some of the limitation of conventional method, especially when we have non-linearity in the system. And that bring up the motivation for us to study, to apply machine learning, to learn and deal with the non-linearity in massive MIMO system. So let me start with a bit of history in wireless communication. And it starts with the first generation, and we move to second generation and third generation. So we have one iteration every 10 years. And you can see that in terms of the mobile phone, it gets started with like a brick, working with analog signals. And then we move to digital communications. And then the mobile phones can be much smaller because of the advance in signal processing and in terms of hardware. And then there was a kind of revolution when we had iPhone that was released, I think in 2005 or so. At that time, it's a 3G network. And then we had 3.5G. And then about 10 years ago, we have 4G LTE network. And then we have another iteration, 4.5G LTE Advanced. So along the way, we see that there's a improvement in terms of the data rate. Right? We start with a kilobit per second, and we go to several megabit per second, and then we go to 300 megabits per second in 4G network, and then 4.5G we move to with all the technologies in 4.5G we can go to 1 gigabit per second. So probably you heard that since last year, we will talk about 5G network. And if we just turn on the TV, there's a lot of advertisements about 5G network. So what makes 5G network different to 4G? The aim of 5G network is to build a network with more capacity. Right? The aim for 1,000 times more capacity to the network. And that requires a lot of advances in technologies for 5G network, wireless technologies. So to aim for 1,000x increase in capacity, they look at more spectrum that could give you 10x capacity. They look at more network deployments, more cells, and some mobility in terms of they deploy ECHO small cells. Right. So to give a bit of the idea how we can increase the data rate or the capacity of the network, I like these pictures. I saw this before, so I just want to repeat it. So basically, we want to send a data stream or data traffic from one end to another end, and we want to increase the amount of traffic. So the way we do, we would build more roads. Well, we put more channels, more medium to carry the information. So that's the theory, but how we can do it? we can build more rows, but we can go wide. So make the row wider. All right. So in this case, we have to look at more. We look at exploit more spectrum, new spectrum. For example, in 5G network, they start talking about millimeter wave. So they want to roll on the band like 28 gigahertz and 39 gigahertz, something that's very high frequency band compared to 4G network when people still use like 900 megahertz or 1.8 to 1.9 gigahertz bandwidth. So that's the M, but at the moment, I think that the current roll on 5G network, they still going, I think it's about 3.5 gigahertz bandwidth. But anyway, this solution can be very expensive because spectrum is expensive. And I think a couple of weeks ago, we will talk about the 5G spectrum auction, and that it can go to billions of dollars to get the license for a particular band. So the other option is that we go height. So in this case, we use spatial multiplexing. So we stack up multiple data stream on top of each other. So you don't need to go for new spectrum. You can utilize the existing spectrum. It's just that you need to stack up all the data streams. So that is the motivation behind MIMO communications, right? So the idea is for one-to-one communication, you can have the capacity just it's scaled by log 1 plus SNR. So you think of SNR as just the row condition, right? Row good, we can have high capacity. Row bad, we go for low capacity. But if we can stack up multiple rows, then you can scale the capacity of the traffic by the number of rows, right? Literally, we can go for the minimum of transmit antennas and receive antennas, right? And of course, the row condition also go into play. So MIMO, the idea is just put multiple antennas, use multiple antennas, and stack up the data streams and send out all data stream concurrently. All right, so MIMO was introduced back in 4G, but then about 10 years ago, people talk about massive MIMO. It just, we go massive. We go, instead of 4 antennas in 4G networks, let's go for 10 to 100 antennas, or maybe 1,000 antennas. And we can support tens of users concurrently, right? So we have more dimension, more rows, so we can put more cores on the row at the same time. So that's a lot of advantage in using CAF redundancy. Right? One way is that we can have high reliabilities in communications. So at one point, of course, we will find out good road to travel, even if there's no blockage somewhere. In terms of probability, we will find out one good road to travel. And due to the redundancy, so even that some rows are blocked, we still be able to send multiple calls at the same time. So we can have high spectral efficiency as well. And, but that's a trade-off. Nothing comes for free, because if we implement multiple antennas, it would create issue with hardware and energy consumptions, because you would build more complicated hardware. It's more expensive, of course, and more components in, it could consume the energy, the battery faster. So when we talk about massive MIMO, we talk about, we scale up in the base station, whereas the power consumption is not a big issue. But at the mobile stations, people would stick with about 4, maximum 2 to 4 antennas, or 2 to 4 data streams at the same time to 1 antennas. I'm not talking about phase array at the mobile station where they can put 100 small antennas. But that is a different story. But anyway, So once we go more antennas, more data stream, of course, the system become more complicated, especially from the signal processing side. So we had to deal with more data streams concurrently. So the question here is, can we achieve good performance from massive MIMO with non-ideal hardware? So non-ideal means that instead of using expensive hardware, we can use low-cost hardware, something with a lot of non-linearity. But the idea, because we have so many components together, even that some components may not be functioning, or there's a lot of non-linearities, not perfect components, because we have redundancy that can help to recover the non-ideal conditions in the hardware. So that back to 2014, there was a study on the efficiency and the limit capacity limit of massive MIMO system, and they say, yeah, massive MIMO can work with non-ideal hardware. So that was the theoretical result, but how to make it work, how to make the signal processing work with non-ideal hardware. So that is there was a lot of ongoing work and the work in the last couple of years to deal with non-ideal hardware. So, so let me review quickly about some of the conventional MIMO signal processing technique. So I want to start with the linear MIMO system first. So a linear MIMO system is the idealistic model. It's just we have a channel input, we have output. So you can think of X here just the call going to the network, H here just the channel or the row condition, and Y here just the calls coming toward the end of the row, and we have the noise. That's the noise coming from the environment. And the whole idea of communication is that given that your observation, what you receive at the other end, can you guess or can you estimate what were being sent out at the beginning? So given Y, how can we retrieve and recover X? And the perfect scenario is that you get X exactly what was being sent at the beginning. So to recover X, the first step we need to do is that we had to estimate the row condition. So we had to estimate what we had to estimate H first. And this can be done in the step we call channel estimation phase. All right, when we send out a no pilot. So any communication system, we put up at the beginning some pilot, some no signal, and that we put in the system. And then at the other end, we know what will be sent. So we use that pilot signal to estimate the channel condition. Right? And this is a very common statistical signal processing step. Right? And then once we know the row condition, then we go to the next step is we estimate what being sent, that the data traffic itself. So I use two different notation here. So T is for the training phase and D is for the data transmission phase. D for data and T is for training. So those tools are the most primitive tasks, the most important tasks in any communication system, not just MIMO. So how, first we need to do channel estimation. So channel estimation is just we need to find an estimator of H, given that your observation during the training phase is the function of what you receive. And in the most common scenarios, when people make a couple of assumptions here, that H, the channel condition is Gaussian, the noise is Gaussian, and in this case, H and Y are being jointly Gaussian. And In that case, the posteriori, so we had the prior distribution for H is Gaussian, and the posteriori distribution for H is also Gaussian. So if we need to do a Bayesian optimal estimator for H, it's fairly easy. We can, because it's Gaussian, so the mean is also the mode of the distribution, and this can be found in closed form. And in our field, we call it the MMSE estimator, minimum mean square error estimator. So for this special case of Gaussian distribution, the linear MMSE estimator is optimal. So you can see that the expression, the estimator is in linear form. Right? So we have some matrix multiplied with what you receive. So linear MMSE estimator is optimal and the performance is predictable. So we can quantify the error in the estimation step. So this is done. So that's why we don't need machine learning here. We can do just statistically, we can derive the solution in closed form. But what happens if y of t, what you receive is not Gaussian, right? Or if the channels, the covariance matrix of the channels. So here the derivation assumes that you know the covariance of the channel. So what happens that the covariance is not known, or what happens if the noise is not Gaussian? Most of the time we assume the noise is Gaussian, but it could be Laplacian distributed, or it could be impulsive noise. So that's the first step. The next step is data detection. So data detection, basically from what you receive, you try to recover what's being sent out. So that is the data. And the optimal decision rule is based on, we use the maximum likelihood detection. So ML here stands for maximum likelihood detection. So we have the conditional probability, right, given X and Y, and then we want to maximize the likelihood. And this is because of the noise Gaussian, and then we can turn out it to be, we call it the minimum distance receiver. The difficulty in this try to do data detection here is because what being sent out here is belong to a discrete set. So the distribution of the transmitted signal is discrete. Sometimes we assume it to be discrete, uniform. So the distribution is discrete, uniform. And in that case, if we want to find the optimal X, we have to look at all possible value of X. And that's why the complexity can go really, really high, because if you scale up the dimension, so each value of X is just the vectors. And if each value have, let's say, is possible 4 values, is a small number. But if we stack up in massive MIMO, you can have 10 users. That fall to the 10. That's the dimension that you, or the search space that you need to find out the optimal value of X. So this is still a difficult problem. It's a very difficult exponential complexity. And we had to go around. So one easy way is that we try to find a linear MMSE detector. It's not optimal. This is because the distribution of X here is not Gaussian. Right? So linear estimators, MMSE detector is easy because it's linear form. And then after you try to guesstimate the solution, and then you can perform element-wise detection. Right? Other methods can give better result, like sphere decoders and many type of lattice decoder can give better performance, but it can, there's a trade-off. Right? So if we go for high complexity, then you should expect better performance. But still, we can see that this is done deal. All right, so the theory on the technique, signal processing technique for MIMO communication pretty much done with this. And we can quantify the performance analytically, all right, how good is the algorithm is compared to the optimal ML detection scheme. So that's done. So here's my view, my perspective, if we look at these two problems, channel estimation and data detection. Right? So we can view this thing from the machine learning perspective, not just the conditional signal processing perspective. So the channel estimation is a regression problem. So basically you have the observation and you want to derive, or you want to use machine learning to find out the mappings from the input, which in this case is what you observe, and try to do regression so that it makes the solution close to the true value of the channel. Right? So this is regression. Data detection here is a classification problem. Right? So we aim to minimize, again, also you use machine learning, try to give the estimate so that is close to the true transmitted data. This is a classification problem because actually it belongs to a discrete set of numbers. Right? But here the number of labels can go really fast. This is because the search space for X, it can go high really fast. So I gave you one example, for example, 4 to the 10, which can go extremely big. Or we can go for a joint scheme. Basically, we look at both channel estimation and data detection problem together. You look at all the observation you can have. So observation during the training phase and data phase, and you put all together, try to learn and provide the estimation for the data, the transmitted data. Because ultimately, our aim is just to retrieve the transmitted data vector. But there's a drawback using machine learning, especially if you build a neural network to do this kind of classification or regression problem. That because if you fix the dimension of the neural network, typically we set how many neurons and how many layers. So that kind of deep neural network, it is not scalable. This is because what happens if I change the number of antennas, the number of input, and I want to have a different number of output? We don't have that luxury if we use a neural network to provide the estimate for the data. Traditional signal processing method, okay, it's just an equation. You just put it there, and it doesn't matter the dimension, as long as the matrix size match with the other, and then you have the solution. The other drawback of machine learning in this case is the wireless communication system is dynamic in the sense that the channel, the row condition can change over time. And if we train the network to do certain tasks, it's likely that the network could be trained on a particular channels only, right, for a particular row condition. So whenever those change, you have to retrain the whole network. And communication is fast. We don't have the luxury to keep training the network. Right? Whenever actually change, you train it, and that's too late. Right? So that's a potential of machine learning. So we are going there. Okay, so in massive MIMO, I mentioned that it could be very expensive. Right? So if you scale it to 10 hundreds of antenna ports, it's not sustainable in cost and power consumption. For example, if we had the ADC, analog to digital converter, the DAC, digital to analog converter, and those are very power hungry components, especially inside the mobile phones. So we look at the alternatives. All right, so we use non-ideal hardware. But in any components in the pipeline of the communication system, so for example, we go for the signal and digital domain, we go for analog domain, we go for mixers, we move it into higher frequency, and then we amplify the signal, and at the other end we had to amplify the received signal again, and then down convert to lower band, and then analog to digital converter back to digital domain. So all these components, it introduce nonlinearity to a certain extent, especially in the digital to analog converter and the analog to digital converter. But if we go for non-ideal hardware, these effects, the effect of nonlinearity, become even more pronounced, especially if we go for low bits quantizer, 1 or 3 bits. So that's a trade-off. We look at non-ideal hardware, cheap, affordable hardware, but then that introduces a lot of nonlinearity. And our task is we use signal processing technique to deal with this nonlinearity. So we deal with what we receive at the other end, at the receiver. Right. So to model the nonlinearity, I go for a very generic modeling. So basically, instead of we send out the signal X, it undergoes a transformation, a nonlinear transformation. So GTX is what truly being sent out at the beginning of the network, right? And what you capture at the end, it also undergoes a nonlinearity process by we model of a function GR, which is a generic function for now. So to deal this scenario, the easiest and the most straightforward way to deal with this system is that we linearize the system. Given GR, GT are nonlinear function, we just approximate into a linear function. And in this case, we can go with the bus gang decomposition. It just, the idea is that if we have an incoming signal or the incoming process, a random process input, and it's go through a nonlinear function, and what you observe is V for now, we can approximate to be linearized is by a linear transformation A times U plus a noise component, or this is the error in the approximation. Right? And the aim is that we decide, we can find out the transformation A so that the error is minimized. Okay. And this decomposition works very well if U here is a Gaussian process. This is, you see the linear transformation, and in my opinion, this come back to Gaussian random variables and linear MMSE estimator, which is optimal for the case of Gaussian. So my guess, my intuition here is that when U is a Gaussian, we can do the linear transformation with the minimum error. Okay, so we can do the approximation. Linearize the system on both ends, transmitter side and receiver side. Eventually, what we coming out here is an approximate model, linear model, which have a channel H tilde, which accounts for the decompositions at the receiver and the transmitters, and the noise component, which account for the noise from the environments and the error due to the approximation, right? So we aggregate all the nonlinearities into the new channel H tilde and the noise tilde. So all the analysis in terms of spectral efficiency for massive MIMO system with nonlinearity is that they base on this approximation and do the analysis. And most of the time they would try to approximate the noise at Gaussian because it's easy. And Gaussian noise is the worst, right? So we just approximate to be the worst case scenario. So, and also in terms of signal processing, we just think of H tilde is the channel and tilde is the noise. And that's it. We can apply whatever method so far in terms of the channel estimation and data detection algorithms. And we go to the result. It works really well, especially at low SNR, low signal to noise ratio. That's my guess. Is because at low SNR, the signal input to the approximation is Gaussian-like. It's like Gaussian random variable or Gaussian process. So the approximation using Bus-Gaussian decomposition works very well. However, at high SNR, the performance is no longer good. There's some certain performance bounds, the error flow that we had to deal with, and it is not good at high SNR. So the question here is, why not? Here is there's a room for us to use machine learning for nonlinear input-output knowledge discovery. Everybody knows that machine learning is really good to learn from nonlinear representations and all that stuff. So why not use machine learning here? So that is our motivation for this work. Let me double check. Okay, we have time. Okay, so the first work we tackle on is we consider the scenario with when we have low resolutions ADC. Okay, at the receiver side, right? So by low resolution, I mean that we have only 1 or 3 bits. So in scenario of 1 bit ADC here is, if I receive the signal which is positive, I say +1. If it's negative, I say -1. So it's a very, very bad nonlinear transformation. Right? Everything is bigger than 0, we say 1. Right? So obviously, when we do this kind of quantization, right, we quantize what we receive. What we observe, this should be Y here. So what we observe in terms of the received signal is just +1 and -1. And of course, Y is not Gaussian, right? It's Bernoulli. So in this case, conventional methods, so far we study, work really well with Gaussian, but in this case, we have a kind of a Bernoulli distributed received signal, and it might not, conventional method might not work well with this nonlinear model. Right? So our first work, we look at, we use semi-supervised learning method. Right? So we're not trying to estimate H. Right? We just try to learn the transformation from the transmitted signal X and the received signal Y. Right? So we ignore the step of finding H. Although, if you know H, we can use maximum likelihood detection. Right? So if you know the row condition, you can use ML condition for finding the transmitted signal H. It's just that it has exponential complexity. Right? So we start with the k-mean clustering method. So in case, this is just one of the basic methods in machine learning. So I just go over it quickly. So basically, we would send out some training signal, is there. And from the training signal, we try to find the centroid for its label, right? Because we said that our transmit signal belong to a discrete set, and each element in the set we set a label, right? And we had to send out all the labels at the beginning first. And from what we receive, we find out the centroids, and then from the centroid we try to estimate classifies for other labels, other data points, and then from those data points we estimate the centroid again. So it's a very common method, the k-means clustering method. Right? And that was our work, and that was, I think, was accepted last year, June 2020, not 19. It appeared last year. So that's the method, common method in machine learning. But what we did extra in the work is that we derive the performance for our proposed algorithm. And it's a bit of weird that in our communication community, whenever we propose algorithm, we have to quantify how good it is. And this is, we have to analyze the performance. Right? We have to give out some bound, exact performance, or the bound for the performance. So it took a lot of effort to find out the bound for these semi-supervised learning methods when we apply into the 1-bit system. Right? One interesting note here is that the error, the errors in detection, it decays really fast. It decays exponentially with the number of received antennas. All right. So this brings us the advantage of using massive MIMO. So as far as you can increase the number of antennas, you can make the performance, the error in your detection drop exponentially fast. All right. So so here is some numerical result from our work. Basically, we compare directly with the ML detection. And here, ML detection, we had to assume the red curve here, that we had to assume that we know perfect the channel condition. Whereas our method, we don't know the channel. We just use semi-supervised learning. And it works, the performance is very well, right? So something drop faster is better. So compared to the same H&R, something that would have lower error rate, that would be better, right? So of course, ML is optimal, so it's the lowest curve here. And then we have our performance, and then we compare with other techniques like zero forcing or ML detection with estimated CSI channel condition. And then we outperform all the scheme, right? And we also present our analytical results. We compare the numerical result, which we run the simulation, and then we compare with what we derive. And it's very, very close. So in terms of analysis, we derive the bound. That is the bound right here. And then the performance, and it's, you can see it's pretty much matched with the bound at high H&R. Okay, so that was one work, but then the method has the limitation because of k-mean clustering. So far in our work, it can only work with small number of labels. This is because of you don't have the luxury in communication system to send out all the training data. Right? You cannot send all labels. If you have 4 to the 10 number of labels, and you have to use a lot of traffic just send out the training data. So that is not efficient. So we had to look at we had to come back and look at the traditional method in MIMO signal processing. That is channel estimation, right? Estimate a row condition first, and then data detection second. So we compare directly with one of the first work in channel estimation for 1-bit system, and this work they use Bus-Gaussian decomposition. Right, it should be all here. I'm sorry. So I mentioned to you the Bus-Gaussian decomposition before. It works really well at low SNR because we have the Gaussian like signal go in. And after that, when we had the linear model, we can use linear MMSE estimator. And it works, again, it worked really well, but then at high SNR, it doesn't. So that's where there's a room for us to exploit. And our work, we rely on the support vector machine for channel estimation. And just a bit of background in case of some of you don't have the background in say, machine learning. Support vector machine is just at the beginning it was a binary classification problem with a training data set. Right, so we have a list of features or predictors, and we have y here is the response. Right? And binary classification means that it plus or minus 1 for the response. And support vector machine helps to find a lie or the data plan, so that can separate the two set of data points, label sets, right? And support vector machine give us the lies that give them highest separation between the two set of data. And there's a formulation for support vector machine. It's a convex problem, quadratic programming, and it's very solution is well known, and it's the linear combination of the support vectors. Right? So there's also some reformulation of support vector machine when we introduce slack variables just to include some misclassification points. So that machine learning. So how it's related to our problem, and that was the work by Van Lee, and he found out that okay, there's a connection there. So what we have here is we have a nonlinear system. So we had some received signal, and that is being quantized into +1 and -1. So from this type set of equation, we had the vectors and we have set of equations. We can think of the transmit signal during the training phase can play as the predictors, all right, or the features, and the receive here is just the response. And pretty much we had the linear equation inside here. So we're not using support vector machine. So we formulate the channel estimation problem using the SVM, and there was no clear connection at the beginning. One point here in support vector machine here is that we try to find the lie or the plan, whereas our problem is that we try to find the channels, the estimated channel, so that it might all the set of equation satisfied. Right? So we have +1, -1, and transmit signal. So those things don't seem to connected to be connected at the beginning. And we, even though we published the papers at the conference, get the best paper award, and I had to admit that it works, but we didn't really we didn't really understand why it works. And we also had a paper that currently been submitted and under revision, and we hope that it get accepted at a journal paper soon. So our current work and ongoing work here is we try to figure out and provide the analytical result why SVM can be used for channel estimation in 1-bit system, why it works technically. So the next step is we also can use SVM for data detection as well. Right? Again, we have linear equations, and then we have quantization step, give us +1, -1. And in this case, we can look at the channels, each row of the channels. Here is the predictors. It's the predictors or the features, and you have Y here is the response. Right? So together is form the training set. And we need to retrieve H of D. Okay. Again, we formulate the an SVM optimization problem. But there's a trick here, because SVM, it just give you the solution. It just give you the data plan to separate the two data sets. But that solution, it does not belong to the discrete set we want. Right? We want the solution must be in the discrete set. So we propose the methods, try to revise the solution, make connection to the discrete set. And we also provide the joint channel estimation and data detection algorithm. So as I mentioned to you, what happened if I had received signal during the training and data transmission phases? Can we do the estimation for the data together with the data from the training phase, right? So here's the numerical result. Let me double check the time. Okay, I'm running out of time. So the key point is that we achieve a really good performance, better performance, about 1 dB performance extra compared to the Buzzcam linearized method, right? But there's some note here that our performance is not better at low SNR. Okay, as I mentioned, low SNR Buzzcam decomposition works really well. So that's in the room that we still looking on. Try to make our method using based on machine learning methods that we provide better solution than the conventional method, linearized methods. And we also do the join method that we take advantage of both the training phase and the data transmission phase, and we can get a much better performance in terms of channel estimation. All right, and we also have the figures, the performance on data detection is also very close to the ML detection, which is optimal. All right, so that was SVM. And then our ongoing work, we look at using deep learning methods for learning the nonlinearities and deal with the nonlinearity in massive MIMO system. So just a very quick recap, what is neural network? So basically we use a neural network as it's like a feed-forward neural network for regression. Right? So we have input go-ins, and we can apply nonlinearity, nonlinear activation functions, and then eventually we try to provide, doing some regression, provide estimations. And actually the deep neural network is an MMSE estimator. So this can be called as the data-driven approach, because we can generate a lot of data synthetically. So we had a model, y equal to x times x plus n, and then we can generate the data for the channels and what you receive, and we use that generated data to train the network. And whenever we receive a new signal, we can use the network to provide the estimate. And for nonlinear system, at worst, the DNN performs like the linear MMSE estimator. That's because if we have only one layer, it just W here is, if you think of the coefficient for one layer multiplied with input, it gives you the estimate output. So if the learning algorithm works perfect, we can find out that matrix. So technically, one layer deep neural network is the linear MMSE estimator. So that's the worst scenario. But then can we do better than that? Can we do better than just simply learning the distribution of the model from the data? So the purpose of the neural network here is we learn the model using the data we have, but in communication system, we already had a model. We established a model, so why don't we take advantage of the model we have? And that could help us to train the network better. Maybe that we come up with the new architectures for the network that performs better, right? So we take the knowledge from the model we have. And in this case, we have some ongoing works that we use DNN as the solution to find the solution for the maximum posteriori estimator, the map estimator. In this case, for channel estimation, we look at the estimated channel as the one that maximizes the log likelihood function. So I break down as the one part here is the log likelihood, the other one is the log of the prior distribution on H. Right? And for data detection, we can also look similar thing. We try to find the optimal solution to one portion is the log likelihood and the other portion is for the prior distribution of the data. And since our data is discrete, so I replace it with the indicator function. So either it's belong or not. So we use the deep unfolding technique. So there was a paper that basically to tell that you can unroll a recurrent network into multiple layers of the feed-forward networks, and you can use the DNN to optimize the parameters of any optimization problem technically. So to find a solution, for example, we can go for gradient descent or method, and during that gradient descent, we had to search for the step size, try to find the best way to arrive to the optimal solution, or at least locally optimal solution. And we can train a network to help us to find, to optimize those parameters. Right? So of this thing, we have one work that was accepted to this year conference ICC, and we also had a journal paper under submission that we use the deep neural network for data detection. So what we do is just we unroll or unfolding the neural network into multiple layers. So for each layer, we have the estimate coming from the previous layer, and then we try to derive some form for the network. And after one layer is provide a new estimate. And all this network, all this connection, it does not come from nowhere. It's not just we just plug the network in and let it run like a black box. And we had to come in from our model, and we derive and what should be the coefficient there and what should be the connection there. So to help us to optimize the parameters in the neural network. Right? And the good thing of the deep neural network detector is it can run in batch. So if you use TensorFlow, you can fit the data in big matrix and they do calculation really fast. So so supposedly if you had deep neural network receiver, you can also do detection in batch, right? So so we have other works also ongoing, these things. The other work is we try to connect together between the DNN approach and the SVM approach. Right? So as I mentioned to you, the SVM work, and we are on the way to figure out why it works and whether it's connected to the DNN. It's going there, and hopefully we will submit another paper, try to reconcile and try to make all the works connected. Right. So I'm right on time. So I had the final remarks here that several signal processing tasks can be performed with machine learning and deep learning. The key point here is that sometimes what we are a bit conservative in the sense we just don't want to throw in the algorithms or the neural network to perform, let's say, channel estimations or data detection without understanding why it works or what should be the network look like. So that is the thing we spend a lot of time trying to figure out the best architectures for our problems. The other one is we also try to make the neural network more scalable. And as I mentioned, if it has fixed dimensions, input and output, can we make it like if I have less number of inputs and if I demand less number of output, how can the network can be designed and trained? We also try to look at the effect of other nonlinearities beyond 1-bit ADC and DAC. So we also have the work if we had to quantize the signal using multiple levels. To me, is if we can model the hardware nonlinearities, and then we can model this thing as the nonlinear activation functions in the neural network. Right? So if you want to optimize one end to the other end of the communication system, so why not just model it layer by layers in neural network? And we optimize the neural network and use that optimized parameters, and that would help you to go back and optimize the parameters for the communication system. Right? The last remark here is the performance analysis is an open question. I mean that sometimes we come up with a good algorithm. Like SVM, it works. We bring up the DNN, it works. But then, can you quantify the performance? Give us the equation. What's the performance bounds? So our communities, a lot of time we had tough reviewers just ask the question, why it works, and give us the bound. And those things still an open question. That's it for my presentations. And we have time, I guess, for questions.
Well, the floor is open for questions. Anybody, if you want to ask a question, just on mic, open the mic and ask your question.
I have a question. On slide 22, does that show the simulation performing better than the theoretical limit? Did I understand that correctly?
The theoretical limit here is the upper bound. So we derive the upper bound. So let me give here. So we derive the upper bound. And the performance is, of course, is when we go to the SNR, go to infinity, we get the performance guarantee that is below the upper bound.
Oh, okay. Thank you.
So that's a good thing, actually, because we said that at worst you would achieve this performance.
Yeah.
Any other questions? Well, in that case, I thank the speaker for a very nice and informative presentation. And thank you everybody for attending, and have a nice weekend. I'll see you all next week.
Thank you, Dr. Castello. Thanks all. Bye.